Hello everybody, welcome back to Calculus 1 Online at FCC. In this lecture, we will discuss the chain rule. This particular concept is one of the most important ones in the study of calculus, so we will spend a fair amount of time working through examples, and then we will continue using this rule throughout the entire class, as well as Calculus 2 and 3. The first thing that I would like to do is to review the idea of function composition. Here you see the notation that we're going to use throughout the lecture. H of x is defined as f composed with g. So this is something we've discussed in college algebra or maybe in pre-calculus. And now let's go ahead and take a look at a couple of examples to refresh your memory about this idea. On the left side, I have some simple functions that we have been working with so far. For example, f of x is equal to x cubed. Okay, so you can think about it as taking x and raising it to the third power. And of course, we know how to differentiate this function. So f prime in this case would be 3x squared. All right, now what if we compare it to this function right here? H of x is 4x plus 5 quantity cubed. Okay, so now you can think about it as the input no longer just x, but rather a linear function of x, 4x plus 5. Okay, what would be the derivative of this function? And that's when we will be applying the chain rule, because h of x is composed of two functions, the linear function and then also the cubic polynomial. All right, let's take a look at the second pair. Here we have f of x equals to sine of x. So the argument of this trig function is just x. And we know how to compute this derivative. So f prime for the second f of x function would be just cosine of x. Okay, over here we have h of x equals to sine of 3x squared. So once again, we have a function composition where f is the sine function and g is 3x squared. Okay, how would we go about it if we were to compute h prime in this case? All right, and then the last pair that I wanted to discuss is the exponential. So f of x is equal to e to the x. And if you compare that to this function, h of x, where e is raised to the function cosine of x. Okay, so these are different in which way? Okay, the exponent of my first function is simply x, while the exponent for the second function is a function of x. Okay, in this case, it's trig, could be anything. All right, now we technically don't know how to differentiate exponential functions just yet, so I'm not going to put that derivative here, but hopefully you get the idea that something else is going on with functions on the right. Okay, they're just a little bit more involved, and they are because they are function compositions. Okay, so let's take a look at the rule. The chain rule says the following: if we have h that's defined to be a function composition, so f composed with g. Okay, and there are two different ways of writing it. So first you can write it as f circle g, right? That's the notation for f composed with g, or simply f of g of x. Then the derivative of h is given by the following product. We compute the derivative of f, so f prime evaluated at g of x times g prime of x. Okay, so that is our general formula that we will be applying. Now, the textbook is going through derivation of this formula. If you're interested in all the steps, you can go ahead and review it. But in general, I am not requiring to know the proof of this formula. Rather, I would like for you to know how to apply it. Okay, and here you see an alternative notation. If you see that either in the textbook or maybe other sources. This is just another way of saying the same thing. Okay, in this case, they call y the function, which is a function of u, and u is a function of x. So I personally prefer this notation right here, and you will see that throughout the lecture and the class, I will be using this notation. Okay, so this is the general rule, and at first it might seem a little strange, but once you see enough problems and work through enough examples, it will become a second nature. Now, here are some steps to follow as you're learning the steps or the process of applying this rule. So first, we want to identify what these functions are. Okay, so what is f and what is g? And I will refer to f as the outer function and g as the inner function. Okay, then we evaluate f prime at g of x. So compute f prime and then evaluate it at g of x. After that, we compute the derivative of g. That's the function that's inside. You can think about it as the inner function. And the last step is put it all together as a product. Okay. Again, this will make a lot more sense once we go through a series of examples. And once you master this concept, you won't necessarily have to follow all of these steps. You will just know how to apply the rule to functions that are defined as function compositions. So let's just go ahead and get into the examples. For the first group of problems, I chose examples where we will be applying chain rule with the power rule. Okay, let me remind you what the power rule is saying. If we have x raised to the n, and we would like to compute the derivative of this, then that would be n times x to the power n minus 1. Okay, and here I have 3 examples. Notice that for the first function, I have a positive integer as my power. For the second example, I have negative integer. And then for the last example, this is technically raised to the power 1/2, right? So in this case, n will be 1/2. Okay, let's go ahead and review solutions to these problems, and you will see that I do follow the general strategy and steps that I discussed on the previous slide. Okay, so the first solution, what do we do here? I identify what f and g are. So f in this case would be the cubic function. Okay, that's my outer function. And then g is this cubic polynomial 5x cubed plus 2. So that's how we define our function h as f composed with g. Okay, the next step is to compute the derivative of f. And we know how to do that. So that's 3x squared. And now I evaluate this function, f prime, at g of x. What does that mean? Okay, so that means 5x squared plus 2 goes everywhere I see x. And that's why I have this expression right here, 3 times 5x cubed plus 2 quantity squared. Okay, next step is to take the derivative of the inside. My inside is 5x cubed plus 2. So the derivative of this, we know how to do that. That's just 15x squared, technically plus 0, but we can ignore that. Okay, so now we have all of our components to put it all together. Okay, so remember what the formula is saying. It's f prime of g of x, and that would be 3 times 5x cubed plus 2 quantity squared times the derivative of the inside function, which is 15x squared. Okay, and now we can combine some terms here. So this would be the final answer. Okay, 45x squared times 5x cubed plus 2 quantity squared. You do not need to multiply that square through. Okay, you can just keep it as is. All right, so take a pause here. If this is your first example of working through a problem, applying chain rule, really take a pause and go through every step, making sure that everything is clear. Okay, let's take a look at the next example. Once again, what do we have here? We have an polynomial inside as our inner function, okay, and our outer function is a power function, right? Except we have negative integer. That's no problem. The rule will be the same. All right, so I'm going to identify what my functions are. So my outer function is x raised to the negative second power. The inner function is 3x squared plus 4x. Okay, so this is how we define our function h of x. It's f composed with g of x. All right, next step is to compute the derivative of the outer function. So that would be negative 2 times x to the negative third power. Okay, once we do that, we plug in our g everywhere we see x. So we get the following expression, negative 2 times 3x squared plus 4x, and this quantity raised to the negative third power. Okay, next step is to compute g prime. So the derivative of the inside, and that is 6x plus 4. Okay, and that is a group, so remember to put parentheses around it. And now we complete our problem. The final step is to compute that product. So I put together these two results. So that would be negative 2 times 3x squared plus 4x to the negative third times 6x plus 4. Okay, you can keep it as is, or you can simplify it just a little bit. So notice what I've done. I distribute the negative 2 through this group right here. So that's where negative 12x minus 8 comes from. Okay, and then I brought this group right here into the denominator. Okay, so that's 1 over 3x squared plus 4x raised to the third power. All right, so that would be the answer. When you're working with problems on Newton-Alter, it's very lenient in a sense that it will take either answer. So if you just plug it in just like this, or simplify it, or maybe factor negative 4 on top, that's fine too. It will accept all answers as long as they're algebraically equivalent. All right, now let's take a look at one more example where we use chain rule with power rule. So here we have h of x equals to x to the fourth plus 3x, and that's raised to 1/2, okay, which is equivalent to taking square root. All right, so what is my solution here? First step, I am identifying what my outer function is, and that would be square root of x, or x to the 1/2. The inner function would be my polynomial of fourth degree, so x to the fourth plus 3x. Okay. Then we compute the derivative of the outer function, so that would be 1/2 x to the negative 1/2. Okay, and evaluate this function at g of x. In our case, g of x is this quantity right here, so we are plugging that expression everywhere we see x. Okay, then g prime, so that would be the derivative of the inner function, is 4x cubed plus 3. And then the last step is putting it all together as the product. Okay, so there it is. You can leave it as is. Okay, so 1/2 times quantity x to the fourth plus 3x raised to the negative 1/2 times 4x to the third plus 3. Okay, or you can clean it up. Okay, that's a personal preference, and write it out like this. So notice what I've done here. I wrote 4x cubed plus 3 in the numerator, and then the denominator is 2 times the square root of x to the fourth plus 3x. Again, either answer will be accepted correctly by both Newton-Alter and me. Okay, so you can just leave it as is over here, or if you like simplifying things and making them look a little bit cleaner, that's fine too. All right, so here are your first 3 examples where we apply the chain rule with power rule. Now let's review the second set of problems where we're applying the chain rule together with the product rule. Let's take a look at the first example. Here we have h of x equals to x squared plus 4x cubed times sine of x. So notice that our first function is the composition of cubic and quadratic functions. Let's take a look at the solution to this problem. The first step that I'm doing is setting up the product rule. So that's what the first line is telling us to do. So this is the product rule. Okay, notice I have my primes for the first function over here and the second. Okay, so now where do we apply the chain rule? We apply the chain rule when we compute the derivative of the first function. And that would be over here. So this is 3 times x squared plus 4x raised to the second power. Okay, so I'm first applying the power rule, times the derivative of the inside, which is 2x plus 4. Okay, and then times sine of x. Now the derivative of sine of x is cosine of x, so that's what we get over here. And the last step that I'm doing is distributing 3, okay, through this linear group right here. So that's where 6x plus 12 comes from. And then I also rearranged my terms a little bit. So my final answer is sine of x times 6x plus 12 times x squared plus 4x quantity squared plus cosine of x times x squared plus 4x quantity cubed. Okay, so this is how I prefer to write it, with trig functions as the first one in the line. So if you want to write it in a different order, that's fine. Recall that multiplication is commutative, so it doesn't matter which order you're going to write it. Now also you might be wondering, should we multiply these powers through? And you don't have to. You can just keep it as is. This is completely fine. And also, you don't need to multiply these two groups either. Okay, so just write them as this product, and as long as it's algebraically equivalent, then you're good to go. That would be the answer. Okay, let's take a look at the next example. Here we have a product of these two functions. So the first one is 3x minus 1. Okay, and then the second function in this case is a composition of 2, right? So we have x squared plus 3x raised to the negative second power. Okay, so now the first thing I'm thinking about it is, okay, I'm gonna need to apply the product rule and also the chain rule to the second function. All right, let's take a look at the solution. Okay, I'm applying the product rule first, so that is my first line. Okay, so here's prime for 3x minus 1, and then prime for the second function. Okay, the derivative of 3x minus 1 is simple, that's just 3. And then the derivative of the second function, this is where we apply the chain rule. Okay, so what do we do? Negative 2 times x squared plus 3x raised to the negative third power. Okay, why is that? So this is negative 2 minus 1, and then times the derivative of the inside, and in this case it's 2x plus 3. Okay, so what do we do here? We need to clean this up a little bit. For the first term, nothing can be simplified, so I just left it as is, and then I pulled out the negative, and I need to put the 2. I missed my 2 when I wrote out the solution. So negative 2 times 3x minus 1 times 2x plus 3 times x squared plus 3x raised to the negative third power. Okay, and again, I'm not going to multiply anything through. If you would like to write this as fractions with positive powers, that's fine as well. Okay, all of these are equivalent, so whichever way you want to write it, this is completely fine. You can just leave it as is. So that's going to be your final answer for the derivative of this function. Okay, let's take a look at the last one. This one is the product of two functions. And both of these functions are function compositions, right? So the first one is the composition of cubic and quadratic. The second function is a composition of square root and then cubic. All right, so the principles will be the same. We will apply the same strategy, except this problem will be just a little bit more involved, a little bit more tedious. All right, let's see what we do here. Okay, the first step is the same. We're going to apply the product rule. I'm abbreviating it as PR, product rule. Okay, the derivative of the first function over here, the derivative of the second over here. So that's my initial setup. And now we apply chain rule twice for each of the functions, right? Okay, one for each function, one time for each function. So let's see, this would be 3 times x squared plus 1 raised to the second power, okay, times the derivative of the inside, which is 2x. Okay, so that would be the derivative of my first function right here. 3 times x squared plus 1 squared times 2x. Okay, so that's that. And then over here, what is the derivative of the square root of 2x cubed minus 1? So that would be 1/2 times 2x cubed minus 1 raised to the negative 1/2. Where does that come from? That would be 1/2 minus 1, right? That's the power rule. So that's why we have negative 1/2 times the derivative of the inside. The derivative of 2x cubed minus 1 is 6x squared. Okay, so that means this is my derivative of the second function by using the chain rule. Okay, so now the last step to do here is to clean up a little bit. Let's see, so what did I do for the first group? I put together 6x, so that's 3 times 2x, and then just rewrote all the other terms. So x squared plus 1 quantity squared times 2x cubed minus 1 raised to the 1/2. You can keep it as just square root. It doesn't matter. I just wanted to have all the powers here. Let's see what happens to the second group. So 1/2 and 6, we can reduce this. So that turns out to be 3. So that's where 3x squared comes from. And then x squared plus 1 cubed times 2x cubed minus 1 raised to the negative 1/2. Okay, and that's it. So that would be your answer here. So notice that fundamentally this particular rule is not very challenging, but it can get really busy. It can get really tedious. We have to kind of pay attention to all of the signs, all of the powers and numbers, and carefully work through these steps. Okay, so that's it. That's your second group of examples where we combine chain rule and product rule. Let's take a look at the group of problems where we will be applying chain rule and the quotient rule. And as you can imagine, it will be pretty much similar strategy as we did with the product rule, except now we will be using the quotient rule. So I have two problems here. The first one is f of x equals to x over x cubed minus 4x quantity squared. So let's take a look at the solution to this problem. We would like to compute the derivative of this function f. All right, so the first step that I'm doing is applying the quotient rule. Let me abbreviate it as QR. Okay, so that would be x prime times x cubed minus 4x squared, and then minus x times x cubed minus 4x squared prime. Okay, and then we square the denominator, so that's where x cubed minus 4x to the fourth comes from. Okay, so that's just me applying the quotient rule. And what about the chain rule? Where would that be applying? That would be for this function over here, right? So the chain rule, I'm going to abbreviate it as CR, will be applied to computing the derivative of the function that's in the denominator, because that is a function composition, right? So we're composing cubic and quadratic here. Okay, so x prime is 1, so that's nice. So that's where this term comes from. Okay, and then what about the derivative of our denominator? So that would be 2 times x cubed minus 4x raised to the first power, right? Because that would be 2 minus 1, okay, times the derivative of the inside, and that is 3x squared minus 4. Okay, so that's what we get here. This is the step where we needed to apply the chain rule. And now the only thing that I can do is just rewrite it as following. So x cubed minus 4x squared minus 2x times this product right here, 3x squared minus 4 times x cubed minus 4x divided by this right here. Okay, now you could reduce it by a common factor here, because we do have a common factor of x cubed minus 4x. Okay, that's completely fine. Or you can just leave it as is. Okay, there's nothing wrong with it. Just leaving it as is. Right? So that's your answer for this function. Let's take a look at the next example. Here we have g of x equals to 7x over square root of 9x squared plus 4. Okay, so again, how do I analyze this function? What do I have here? First, I have a ratio of two functions, so that means I will need to be applying the quotient rule. Okay, and then the function in the denominator is the composition of two, so I have quadratic as the inner function and then square root as the outer function. Let's go ahead and compute the derivative of g. The first step is to apply the quotient rule. So that's my first line in the solution. So here's the prime of the first function, and then here's the prime of the second function. We have difference in the numerator, we have square in the denominator. Okay, so all of the components of applying the quotient rule. Okay, the derivative of 7x is 7. The derivative of the square root of 9x squared plus 4. So that's where we apply the chain rule, right? So that would be 1/2 times 9x squared plus 4 raised to the negative 1/2. Okay, so that's me applying the power rule first. Then we need to compute the derivative of the inside. So times the derivative of the inside is 18x. And that's where this comes from. Okay, now square root and squared in the denominator, they cancel out. So we just get 9x squared plus 4 on the bottom. And let's see, what can we do here? So nothing for the first term. I'm just going to leave it as is. And then here, 1/2 and 18. So I reduced it. So this becomes 9. 9 times 7, that would be 63. So we have 63x squared times 9x squared plus 4 raised to the negative 1/2. Okay. And that's it. You can keep it as is. Okay, there are ways to simplify it or maybe reduce it, just rewrite it slightly differently. You don't need to worry about it. Okay, this is perfectly fine. I will accept it as a fully correct answer. Newton Alta assignments, they will also be accepted for full credit. You might notice that the solutions for Newton will look slightly different because they do go the extra step of completely simplifying it and reducing everything they can. That's fine. You can try and do it, but a lot of times that leads to making extra mistakes. So I am perfectly fine with you just leaving this as is. Okay, so that is your set of examples where we apply the chain rule with the quotient rule. Now let's review problems where we're working with chain rule and trig functions. The first function is cosine of 2x cubed minus 4. So how do we compute the derivative of this function? Let's take a look at the solution. The first step is to compute the derivative of cosine, and that is negative sine. Now evaluate it at the inner function, that would be negative sine of 2x cubed minus 4, and then times the derivative of the inside, so the derivative of 2x cubed minus 4, and that is my first line over here. Okay, then the derivative of the inner function is easy, that is 6x squared, so that's where this term comes from, and then we put it all together as the final answer here. This is negative 6x squared times sine of 2x cubed minus 4. Now I want to take a pause here and mention a fairly common mistake that can happen. So I would like you to keep that in mind and try to avoid this. Sometimes I will see an answer that looks something like this, negative 6x squared times sine of x. And that will be marked incorrect because notice what happened here. The derivative of cosine was computed correctly, and then the derivative of the inner function is also computed correctly. However, then the argument of our function is changed, okay? So we cannot do this. We must evaluate our trig function at the inner function, right? So we cannot just write it as x, okay? It has to be 2x cubed minus 4. Okay, and I think this comes from just the habitual of writing, you know, sine of x, tangent of x. We are just not used to having a different argument of the trig function. So I understand where that comes from, but this will be marked incorrect. So just be very, very cautious when you compute derivatives of trig functions. Okay, so for the first example, what did we have? We had function cosine, that was the outer function. Okay, and the inner function was the cubic polynomial. Okay, so that's what we had here. Now for the second function, we have 6 sine to the 4th of x. So for this function, I'm going to go ahead and write it like this. This is 6 times sine of x raised to the 4th power. Okay, so now the argument of the function is just x, but sine is raised to the 4th power. So what do we have here? We have the power function as the outer function and sine as the inner function. Okay, how do we compute the derivative in this case? Here is the solution. So g prime is the derivative of 6 sine to the 4th of x. Okay, I'm going to pull the 6 out. Okay, that's one of the rules that we know we can do. And now I'm applying the power rule first. So 4 times sine of x cubed times the derivative of sine. Okay, we know what the derivative of sine is. That would be positive cosine. So the final answer is 24 sine cube of x times cosine of x. Okay, so that is your first example where we see a trig function raised to a power, and that's how we would deal with it. You can think about it as stuff raised to the power of 4. So the derivative of stuff, so to speak, would be 4 sine cube, okay, times the derivative of sine, which in this case, it's, of course, it's cosine. All right, so now let's take a look at the last example here. And before we compute the derivative, let's break it down. What do we have? We have cosine of 4x plus 2, and this raised to the cubic power. So we have several functions composed here. And you can think about it as the cubic function is the outermost, okay? So that would be the outer function. Then we have cosine inside, and then inside cosine, there is a linear factor, 4x plus 2, okay? So how do we approach computing h prime in this case? Well, let's work through the solution carefully. Okay, so first I'm applying the power rule. 3 times cosine squared, right? So that's 3 minus 1 of 4x plus 2. Okay, so that's me applying the power rule times the derivative of cosine of 4x plus 2. So that's the chain rule applied for the first time. Okay, so the derivative of cosine of 4x plus 2, so that would be negative sine, that's the derivative of cosine, of 4x plus 2 times the derivative of the inside, 4x plus 2. So we applied chain rule twice. We applied chain rule over here and over here. Okay, so the derivative of 4x plus 2 is 4. So 4 times 3 and then times negative 1 over here. That's where negative 2 comes from. Okay, and now I write out the rest of my terms. So that would be sine of 4x plus 2 times cosine squared of 4x plus 2, or you can write them in different order. That doesn't matter. Okay, it's all going to be equivalent, but that is what we have to do here. We apply chain rule several times. Okay, so notice that the last example is kind of like a combination of the first and second example, where we have both scenarios. We not only do we have an argument of the trig function that's different from x, we also have our trig function raised to a power. Okay, so my recommendation is to carefully go through these solutions one step at a time, making sure that every step is very clear, because as you probably have noticed, it can get a little tedious. Okay, it's easy to lose terms and constants and minus sign or negative or plus sign. Okay, it's easy to kind of get off track. So solving these problems will just require a little bit of patience. Okay, so that's your trig functions and chain rule. So let's take a look at an example where we would like to compute the derivative of a function at a value by using a graph. So you will encounter a similar example on your online homework. Let's see what we have. We have two functions, f and g, and the graphs given to us below, and we would like to compute u prime of 4, where u is defined as f composed with g. So how do we do this? Here is my solution. The first step that I'm doing is writing out the chain rule. So u prime is f prime of g of x times g prime of x. This is just the definition, right? So this is just the actual rule that we've discussed at the very beginning of this lecture. And now I'm plugging in 4. So because I need to compute u prime of 4, so u prime of 4 will be f prime of g of 4 times g prime of 4. Okay, so that's what I need to compute, and I'm going to compute each of these values one step at a time. All right, so the first step is g of 4. Well, what is g of 4? That would be this point right here that I'm marking on the graph. Okay, I'm looking at the value that I get here, so that would be 2, right? It's on the vertical axis. So that's what this 2 represents. It's the y coordinate of that point on the red line. Okay, so that means what? F prime of g of 4 is equal to f prime of 2. Okay, so f prime of 2. What do? I'm looking at 2 now. 2 acts as x. Okay, and if I need to compute the derivative of my function f at that point, what I'm really computing is the slope, right? The graph of this function is telling us that our function is decreasing at that point, and because it's a linear function, the rate of change is constant. Okay, you can basically think about it. What is the slope of this line right here? The slope is -2. Okay, now what about g prime of 4? So now I'll go back to x as being my value. So g prime of 4, what am I looking at? So here's my x is equal to 4. Okay, what is the slope of this red line when x is equal to 4? Well, it's also 2. Okay, but notice these two values right here, they represent two different things. One is the y value, the other one is the slope. Okay, and now I put it all together. All right, so -2, that is f prime of 2, that's this number right here, times +2, and that would be g prime of 4, and the final answer is -4. So u prime of 4 is -4. That is the answer that you would be entering here. Okay, so this problem requires our attention here to write out everything very carefully and one step at a time, find the value of each component. So that's what you would have to do to answer this type of question. Let's take a look at a set of problems where we would like to use the chain rule and tables. So this is something you will encounter on your homework as well. All right, so given the table of values below, we would like to compute h prime of 1, where h is a function composition, and that is g of x times f of x. So notice that this composition is a little bit different from what we've seen so far. Inside the composition, we also have a product. So how do we deal with that? Okay, let's go ahead and take a look at the solution. The first step is to apply the chain rule to h of x. Okay, so what would that mean? So I'm applying the chain rule, so that would be g prime of x times f of x times the derivative of the inside. So my inside function is actually a product of x and f of x. Okay, so what do we do now? Now we need to apply the product rule to x times f of x, and that would be x prime times f plus x times f prime. Okay, so that is the first step for us to write out. And I know this doesn't seem very intuitive, and that's why I'm going through this whole process of explaining every single step and how to approach this problem. Okay, so now that we have our general formula set up, we can retrieve the values from the table and compute the numerical value. Okay, so remember x is equal to 1, and also x prime, that's just 1. Okay, so what do we have here now? 1 times f of 1, and then over here we have f of 1 plus 1 times f prime of 1. Okay, and now we compute all these values from the table. So what is f of 1? F of 1 is 1. 1 times 1 is still 1. And we know the value for g prime of 1, that is over here, that is +3. Okay, what happens for the second group? Here we have f prime of 1, and that is -6. So 1 plus -6, that's -5. That's where this number comes from, and that is equal to -15. Okay, so that is your first problem where we apply chain rule to compute the value of the derivative when we're only given certain numbers, certain values. Okay, and I know it is not very intuitive, so I definitely recommend going through every single step carefully and understanding where each value comes from. So that's the first example. Let's take a look at the second example. This one is similar, slightly different product. So notice what we have here. H of x is g of this product right here, x squared times f of x. Okay, so our inner function is a product. Okay, so that's what you need to kind of recognize. So how do we approach this problem? Similar way. First, I'm just going to write out the general formula, applying the chain rule. This would be g prime of x squared times fx times x squared times f of x prime. Okay, so that's our setup. Now we apply the product rule to this derivative right here, and that would be 2x times f of x plus x squared times f prime of x. Okay, so I want to emphasize that this step is crucial in finding this derivative correctly. Okay, we need to recognize that we have the product inside the inner function, right? So that means we need to apply the product rule. Okay, so once that's done, we can compute all the values, right? So x is just 1, so that's 1 squared over here. F of 1, that's also a table value, so we have that one. 2 times 1 times f of 1, and then 1 squared and f prime of 1, that's 6. We know all of these values. So now you just take the values from the table, plug them in. Okay, so g prime of 1, where is that? That would be this value right here, so that's 9. Okay, and f prime of 1, that is 6. Okay, 2 times 1 plus 6, that's 8. So that's where this comes from, and 9 times 8, the final answer is 72. Okay, so here are the two examples that you will encounter on your homework with maybe slightly different variations for numbers, but this is how you would approach these type of problems. I'd like to finish this lecture with the solution to a typical problem in calculus, and that is computing the equation of the tangent line. So here we would like to find the equation of the tangent line to the graph of the function y equals to 3x plus 1 over x quantity squared at the point A with coordinates 1, 16. Okay, so a typical problem, we've done this kind of problem many times. So now we just have a little bit more complicated function where we can apply the chain rule. All right, so here is my solution. I'm computing y prime first. So that would be 2 times 3x plus 1 over x raised to the first power, right? So this is me applying the power rule, times the derivative of the inside, which is 3 minus 1 over x squared. Okay, and you can just keep it as is. You do not need to multiply this through because we're just looking for the derivative of this function at a given point. Okay, so the derivative is computed, and now I need to find the slope of my tangent line, which means I need to evaluate my y prime at x equals to 1. Okay, so once I do that, I get 16. Okay, so that means my slope is positive. So at that value of x, the function is increasing. It is pretty steep, right? So 16 is fairly large number, all right? So that just kind of keep that in mind as we're going to check our answer with the graph. Okay, and then the last step is fairly straightforward. We plug that into our equation. of a line with the given slope and the given point. So y minus 16 equals to 16 times x minus 1. That simplifies to the following equation. Y is equal to 16x. So that is the equation of the line that's tangent to this function at the point A. Okay, and I have this habit of checking my work with the graph. So I plot this in Desmos, and this is what we get. Okay, so we have our function y in red. That's the graph of this function. And I have my point 1, 16. Okay, that's marked on the graph. And once I graph y is equal to 16x, I see that it is indeed the tangent line. Okay, so that's not a bad idea to check your work with either a graphing calculator or Desmos or any other graphing utility. All right, so this is our big lecture on the chain rule. Okay, again, I want to emphasize this is one of the most important rules when it comes to differentiation. You will be using this rule a lot for the rest of this class, and if you continue your study of mathematics, it will just kind of be there every time you need to compute the derivative of a function. So it is important for us to fully understand the idea and how to compute derivatives of functions compositions. So thank you for watching, and I'll talk to you next time.